Welcome to the next lecture of Polymer Process Engineering. Here we are going to discuss the different characteristics of the polymers. As we briefly discussed a lot of the classes of the polymerization in the previous lecture, apart from this we discussed about the various polymerization techniques and some of the commercial polymers. Now the purpose of the discussion about these commercial polymerization commercial polymers was that you can have a brief idea that how important these polymers are and in different segments how these polymers are in use. In this particular chapter we are going to cover the different characteristics of the polymers, the molecular weight and a molecular weight distribution. You see the molecular weight plays a very vital role. We will discuss that to assessing the different properties of the polymer, and because these are the chain components, then there is a distribution, molecular distribution, there is a range of this molecular weight which we are going to discuss in this particular segment. Let us talk about the characteristics of the polymers. Now these you see that these polymers are the giant molecules. They have a large number of important structural characteristics which usually determines or triggering effect about the end use of these polymers with respect to the mechanical, electrical, thermal, chemical and other optical properties. Now some of the properties they are enlisted like molecular weight distribution, degree of branching, degree of cross-linking, polarity of these polymers chains, flexibility of the polymer chains, macrocrystallinity of the structure, fine crystalline structures, different type of the orientation, as we discussed that these polymers are composed of the different type of polymer chain. So how these polymer chains are oriented. So these are some of the main characteristics, and these characteristics is basically depend on the intermolecular forces for a particular given polymer. These intermolecular forces are additive and they give the polymer to their peculiar end use properties. So let us talk about the molecular weight. Now molecular weight of the polymer is extremely important in the polymer synthesis and application. Now usually the scientists use the term molecular weight to describe the size of a molecule. Now the more accurate term is the molar mass, and usually they are referred as a gram per mole. The term molecular weight is the ratio of the average mass per formula unit of a substance to 1/12 of the mass of an atom because of carbon atom, and it is dimensionless. The most important mechanical property, this depends on a very considerable molecular weight which is seen in this particular figure. Now there is a minimum polymer molecular weight that is referred as A, and usually the 1000 to produce any significant mechanical strength at all. So you see that the molecular weight and the mechanical strength, these two things are interrelated. Now above A here, the strength increases rapidly with the molecular weight until it reaches a critical value. Now that is referred as a B in this particular curve figure. The mechanical strength increases more slowly above B and eventually reaches to the limiting value at C. So this is the triggering point where you need to assess that whether further polymerization is essential or not. Now the critical point is generally correspond to the minimum molecular weight for a polymer to begin and exhibit the sufficient strength that to be useful. The most practical application of polymer, this requires high molecular weight to obtain the high strength. The minimum useful molecular weight at B, this particular juncture, usually in the range of 5000 to 10,000. This differs for different polymers, depends on the different chains, etc. Now this generally, this particular figure which we discussed in this slide, generally shifts to the right as magnitude of the intermolecular forces decreases and the polymer chains with stronger intermolecular force. Like polyamides, polyesters, they develop a sufficient strength. This is to be useful at a lower molecular weight than polymer and having the weaker intermolecular forces for like in polyethylene. Properties other than strength also show a significant dependence on molecular weight. The most properties, this show the different qualitative or quantitative dependencies on molecular weight. Few property may increase with the molecular weight to a maximum value and then decrease with the further increase in the molecular weight. Now, that is why the molecular weight is very important. Processability usually begins to decrease past some molecular weight as the viscosity becomes too high and med flow too difficult. So, you need to have a proper or appropriate or optimum molecular weight to make the polymer processable. The practical aspect of polymerization, this requires one to carry out the process to obtain the compromised molecular weight, which is a molecular weight sufficiently high to obtain the required strength for a particular application without overly sacrificing other properties. Now see, this is an art, because the polymerization process is an art to make the monomer polymerizable. Now second thing is that you created a polymer, but to make that particular polymer a processable, that is again an art. At what time you need to truncate the reaction, this is an art, so that this particular polymer must possess the molecular weight which is required to have the proper strength and proper properties. So, this is an art. Now, synthesizing the highest possible molecular weight is not necessarily the objective, because if you go for further higher molecular weight, it may not become be processable and other properties which are desired properties may get altered. The utility of the polymerization is mainly reduced unless the process can be carried out to yield the specified molecular weight. The control of molecular weight, that is why it is very essential for the practical application. Now, if we say that the molecular weight of a polymer, one means there's something quite different from which applies to the small sized of compound, where you have the fixed molecular weight, but here you will have a range of the molecular weight. So, the polymer differs from small sized compounds in that they are polydispersed, heterogeneous in molecular weight. Now, the polymers in their purest form, they are the mixture of molecules of a different molecular weight. The reason for this polydispersity lies in the statistical variation presence of the polymerization process. Suppose we start like this is my monomer, and if it reacts with different monomer, it forms the say P2, like P1 and P2, and this P2 may react with either P1 or it may react with P2. So, it may form either P3 or it may form P4. This contributes the reaction mass. So, it may have molecular weight different, it will have different, and this contributes the entire polymer mass, and that is why this is there is a range within the polymer required, because you cannot have a unique number of monomer in that particular chain. Now, and this contributes the molecular weight. Now, the control of molecular weight and the molecular weight distribution is often used to improve the certain desired physical properties in the polymer product. So, different methods based on the solution properties, they are used to determine the average molecular weight of a polymer sample. Now, we can use the different molecular weights, number average weight, average molecular weights. We will discuss all these things in due course of time. Now, this includes the method based on the colligative properties, light scattering and the viscosity. And there are various methods, they do not yield the same average molecular weight. Now, different average molecular weights, they are obtained because the properties being measured, they are biased differently towards a different sized polymer molecule on a different sample, as we discussed in the previous slides. There are some methods biased towards the larger sized polymer molecules, while other methods they are based towards the smaller size molecules. The result is that average molecular weight obtained the correspondingly biased towards the larger or smaller sized molecule, and that is why the term average molecular weight came into existence. Now, there are various ways and through which you can find out the average molecular weight. One is the number average molecular weight and sometimes represented as Mn. Now, this is determined by the experimental method that counts the number of polymer molecules in a sample of a polymer. This method of measuring this Mn are those that measures the colligative properties like lowering of vapor pressure osmometry, freezing point depression, that is cryoscopy, the boiling point elevation, ebullimetry, and osmotic pressure, that is membrane osmometry. So, the number average molecular weight is mathematically represented by this formula, where the summation of overall different size of polymer molecules ranges from x is equal to 1 to x is equal to infinity, and nx is the number of moles whose weight is mx. The most common method of measuring the number average molecular weight, they are the membrane osmometry and vapor pressure osmometry, since reasonably reliable commercial instruments are available for those methods. Now, the vapor pressure osmometry, which measures the vapor pressure indirectly by measuring the change in the temperature of polymer solution and dilution by the solvent vapor, and this is generally useful for the polymers with the number average molecular weight below 10,000 or in the range of 10,000 to 15,000 range. Membrane osmometry is limited to the polymers with the number average molecular weight is above the range of 20,000 to 30,000 or below 5 lakhs. The lower limit is the consequence of the partial permeability of available membranes to smaller size polymer molecules. Now, above molecular weight of say 5 lakh, the osmotic pressure of polymer solution becomes too small to measure accurately. End group analysis is also very useful measurement for determining the number average molecular weight for a very limited number of polymers. Now, example like the carboxylic end group of the polyesters can be analyzed by the titration method, and carbon-carbon double bond and groups can be analyzed by NMR. Light scattering. Light scattering by a polymer solution, unlike the colligative properties, is greater for larger sized molecule than for the smaller sized molecule. The average molecular weight obtained from the light scattering measurement is the weight average molecular, and which is referred as MW, where here in this formula, this you can determine the weight average molecular weight, where Wx is the weight fraction of the molecules whose weight is mx. Now, this weight average molecular weight can be determined by this mathematical formula. Here, this Cx is the weight concentration of mx molecule, which C is the total weight concentration of the all polymer molecules, and this you can seek the help of this relationship Wx is equal to Cx over C, and Cx is the nx mx. Now, since the amount of light scattered by a polymer solution increases with molecular weight, this method becomes more accurate for higher molecular weights. Now, there is no upper limit for the molecular weight that can be accurately measured except the limit imposed by insolubility of the polymer. So, the lower limit of weight average molecular weight by the light scattering method is close to 5,000 to 10,000. Now, below this molecular weight range, the amount of scattered light is too small to measure accurately. Now, this is the typical diagram of light scattering photometer, which is very common. Now, solution viscosity is also useful for the molecular weight measurement. Now, viscosity, like light scattering, is greater for the large size polymer molecules than for smaller ones. Now, the solution viscosity does not measure the weight average molecular weight, since the exact dependence on the solution viscosity on molecular weight is not exactly the same as light scattering. Now, solution viscosity measures the viscosity average molecular weight and referred as MV. So, you can determine the viscosity average molecular weight through this mathematical formula. Here, this A is constant and the viscosity and weight average molecular weight are equal when A is unity. Now, this viscosity average molecular weight is less than weight average molecular weight for the most polymers. Since this is A is usually ranges from zero point 0.5 to zero point 0.9. Now, viscosity average molecular weight is much closer to weight average molecular weight than number average molecular weight, and usually within 20% of weight average molecular weight. The value of uh, A is dependent on the hydrodynamic volume of the polymer and the effective volume of the solvated polymer molecules in solution, and varies with polymer, solvent and temperature. So, these three are the essential parameters. More than one average molecular weight usually is required to reasonable characterize a polymer sample. So, there is no such need of a monodispersed product like one composed of the molecules whose molecular weights are all the same, for which all three average molecular weights are the same. So, the situation is quite different for a polydispersed polymer where all three molecular weights are different. Now, for polydispersed polymers, with the differences between the various average molecular weight increasing as the molecular weight distribution broadens. So, weight average molecular weight is greater than the viscosity average molecular weight, which is also greater than the number average molecular weight. Now, this is the typical polymer sample will have a molecular weight distribution which is shown in the figure, and the approximate position for the different average molecular weights are indicative in this distribution curve. You see, this is the weight fraction and a molecular weight. So, the maxima is approaches with the number average molecular weight, and viscosity average and weight average molecular weight are a bit closer. So, for most practical purpose, one usually characterizes the molecular weight for a polymer sample by measuring the number average molecular weight and either weight average molecular weight or a viscosity average molecular weight. Now, viscosity average molecular weight is commonly used as a close approximation of weight average molecular weight, which here you can see. In most instances, one is concerned with the number average molecular weight and weight average molecular weight of a polymer sample. Now, this one, the number average molecular weight is biased towards the lower molecular weight fraction, while the latter is based on towards the high molecular weight fraction. So, the value of weight average molecular weight and number average molecular weight would be unity for a perfectly monodispersed polymer, and the ratio is greater than unity for all actual polymers and increases with the increasing polydispersity. The characterization of polymer by number average molecular weight alone without regard to the polydispersities can be extremely misleading, because it will not give the complete information. And most polymer properties such as strength, melt viscosity, they are determined primarily by the size of the molecule that make up the bulk of the sample by weight. Now, the polymer properties, they are much more dependent on the larger sized molecule in a sample than on the smaller ones. So, let us take the example, the hypothetical mixture containing 95% by weight of molecules of molecular weight say 10,000 and 5% of molecules of molecular weight of say 100. The low molecular weight fraction might be monomer, a low molecular weight polymer, or simply some impurities like we discussed, that P2, P3, like this up to Pn. In addition to the different average molecular weight of a polymer sample, it is frequently desirable and necessary to know the exact distribution of molecular weight. Um, we have already discussed that there is a usually molecular weight range for which any given polymer property will be optimum for a particular application. So, you cannot go on increasing the molecular weight, because some of the property may get reduced or sometimes the processability may be very difficult. So, the polymer sample containing the greatest percentage of polymer molecule of the size is the one which have the optimum value of the desired properties, and this desired properties attributes to the processability aspect, to the other aspect which can be which can make that particular polymer useful. Since the sample with the each same average molecular weight may possess the different molecular weight distributions, information regarding the distribution, this allows the proper choice of a polymer for optimum performance. Various methods they have been used in past to determine the molecular weight distribution of a polymer sample. This including the fractional extraction, fractional precipitation. These methods which we discussed, they are laborious, and determination of the molecular weight distribution are not routinely performed. So, once the size exclusion chromatography or the gel permeation chromatography, these techniques developed, and apart from this, the availability of various automated commercial instruments, they have changed the entire situation. And now we can precisely predict the different range of molecular weight for a particular polymer sample. Now, the size exclusion chromatography, this involves the permeation of a polymer solution through a column packed with the microporous beads of cross-linked polystyrene. The packing contains beads of different size of pore diameters, like small beads. The molecules they pass through the column by a combination of the transport into through a beads and through the interstitial volume, this volume between the beads, like this is the closely packed beads, and this is called the interstitial volume, this the space between the beads. Now, molecules that penetrate the beads, they are slowed down more in moving through the column than the molecules and that do not penetrate the beads. In other words, the transport through the interstitial volume is faster than through the pores. Now, the distribution of molecular weight in a typical polymer sample is sometimes referred as the small size polymer molecules. They penetrate all the beads in the column, since their molecular size, that their hydrodynamic volume is smaller than the pore size of the beads with a smaller size. In that case, these beads these acts as a mesh to screen out the smaller molecular weight polymers. A larger size molecule does not penetrate all the beads, since the molecular size is larger than the pore size of some of the beads. The larger the polymer molecule weight, the fewer beads that are penetrated and the greater is the extent of transport through the interstitial volume. So, the time of passage of the molecules through the column, this decreases with the increasing molecular weights because of the heavy character, and that is screen out. The use of appropriate detector is very important, how to detect the things, and the refractive index, viscosity, light scattering, these measures the amount of polymer passing through the column as a function of time. So, not only does the SEC yields the molecular weight distribution, but the number average and weight average, also the viscosity average, they are also calculated in situ. Size exclusion chromatography is now the method of choice for the measurement of number average and a weight average molecular weights. Now, this size exclusion chromatography instrument is far easier to use compared to the method which were used like osmometry and light scattering. Another method which is being widely used for the measurement of molecular weight is the measurement of viscosity. There are different type of viscometer available. This is done by measuring the viscosity behavior of a polymer in a dilute solution, and these measurements are usually made at constant temperature in a capillary viscometer. These are the capillary viscometer enlisted. This one is Ostwald viscometer and this is Abel-Hood viscometer. Other widely used technique for the measuring of molecular weight is the osmotic and the light scattering methods. Now this osmotic method, they are carried out in the units which is shown here. Uh, the next, that is light scattering method, is used in the light scattering photometer. Now this is the Zim-Myerson osmometer. Now the procedure is quite simple. It is used to determine the molecular weight, to carry out the test at various concentration levels and then extrapolate the data to the zero concentration like here. So this, by this way you can calculate. Now this is the plot for the molecular weight determination of the osmotic pressure for nitrocellulose in acetone, methanol and nitrobenzene. Now this is the plot for the molecular weight determination of the cellulose acetate fraction by the light scattering. Here you see the concentration and this is this one. Now the intercept of osmotic pressure, here you see data. The osmotic pressure divided by the concentration gives the RT over Mn is the number where Mn is quite obvious. This is the number average molecular weight. Likewise, the SC or R, this intercepts where H is the constant, C is the concentration and T is the turbidity, and this gives the value of 1 over weight average molecular weight. Now, let us talk about the molecular weight distribution. As in brief, we discussed that why we are more worried about this particular thing, because in a particular mass you will find the monomer, you may find dimer, you may find trimer, you may find different type of a polymer. So that's why it represents a molecular weight distribution. So the average molecular weights, which we discussed in a couple of slides ago, this characterizes the average degree of polymerization for the mass. It is also important for, in many instances, to know the distribution of the molecular weights in the sample. Now such distribution, this gives the frequency of occurrence of a certain degree of polymerization. Now such a distribution of the frequency of occurrence of a certain degree of polymerization. Now here you see the typical distribution curve for two polymers which are shown. This is the high molecular weight and this is the low molecular weight, and this is the viscosity and the shear rate. You can see the effect of molecular weight for different molecules. Another method of presenting molecular weight distribution is by the cumulative curve. Here you see that this is the molecular weight and the cumulative weight percent, and you can draw the curve like this and you can predict the behavior of the polymer. There are a number of methods for determining the distribution of molecular weights. The principal methods, they are like fractionation, sedimentation, GPC or gel permeation chromatography, or rapid estimates. The fractionation, this consists of separating a polymer solution into the separate groups by fractional precipitation and then measuring the mass and average molecular weight of the fraction. The sedimentation, this uses the ultracentrifuge to determine the number of different molecular weights. GPC, this we have already discussed. This polymer samples, they are separated by the size of molecules. Here you see the different beads and you see that here the separation begins and here you find the separation completed. The separation is accomplished by using the beads of a resid, and obviously these are some sort of polymers, and these are the porous gel, which pores are about the same size of the polymer molecule dimension. Now methods are also available for the rapid estimation of a polymer molecular weight distribution. Now these methods include the swelling, in which the amount of polymer precipitated with respect to the non-solvent added, this gives the cumulative distribution curve. Like higher molecular weight first precipitates out with the non-solvent addition. Then turbidimetric titration, which uses the turbidity induced by the non-solvent addition as a measure of molecular weight distribution. So in this particular segment, we discussed about, because see, molecular weight plays a very vital role in deciding the properties of polymer. So how we can determine the molecular weight, what is the role of molecular weight distribution, and what are the different type of molecular weights. So in this particular chapter, we have discussed all about this particular thing. For your convenience, we have enlisted couple of references. You can use these references as per your need. Thank you very much.